Okay, so we have considered now we have constructed the uh, state transition diagram, which is a little bit complicated, and we found that we can represent the same thing with our state table as well, right? But now we are concerned that can't we just complete it using this one? Do we need that extra two states, right? So maybe you can't even fathom that we can actually build it using this table only, right? But it could be a little bit complicated, right? So how can we analyze this one and see whether we can simplify it? Okay, for simplification there are concept called equivalent states. Okay, what do you mean by equivalent states? So let's assume there are two states in our state transition machine, and or state transition diagram. It could be any of these, right? So the idea is if S1 and S2 is producing the same value at the state machine output, right? For example, what is the output in our state machine here? Z, right? So uh, any of the two states have a chance of being equivalent only if our z is similar in each one of these, right? So now maybe one of these are equivalent to the others because I have z equals 0 on all of those, right? How about this one? So here z is 1, that means I have a chance of any of these two states being equivalent here as well. Okay, so what is the second condition? So for each input combination in S1 and S2, there must have either the same next state or equivalent next states. So that means I have outgoing transitions from each one of these states, right? So if these outgoing transitions are based on some kind of input combination, right? So these are the input combinations, right? So if my all of my for all of my input combinations, I get uh, the same landing state, right? In that case, I can say my two states are equivalent, right? For example, let's consider this one. So let's consider the first one. Okay, I have a naught here, a naught here, but the second part it's landing at a different place, right? So probably it's not equivalent, right? So let's come here, and I have a naught naught, and I have, okay, so if I consider this row and this row, actually it is indeed the same, right? As you can see, these two are in the same landing states, right? So and my output is also 1 in both cases, right? That means my a00 and OK a0 are equivalent states. Okay, so this is and this is these two are equivalent states. So if you look through A11 and OKA1 also, you can see this and these are actually the same, right? So I can say that these two are also equivalent states. So in state diagram, this might be quite difficult to see, right? But if you just carefully consider what are the output conditions from here and here, you can see that okay, maybe it's equivalent, right? So 1110 it's landing here, 1110 is landing here, right? For 00 it's landing here, for 00 it's landing here, right? So what else is remaining? 10 is landing here, 10 is landing here, right? So similarly, so because of this you can just replace or bind these two together and it will be a, same state, right? So that's the idea. So you can do to both of these pairs and combine them in a single state transition table. So I have named them OK0 and OK1, and you have to rename entire thing because now for first two rows actually I have A00, right, but I have renamed it to OK0 now, and OK1. So you have to rename that with the replaced state names, right? So you will get a simplified uh, state table now. Now I had four uh, states which can provide me with z equal 1, but now I have only 2, but this is already satisfied all the conditions because of this state equivalence. Okay, so now I can again draw my state transition diagram if you would. So the idea is that in here, uh, whether the init state is necessary or not, right? Let's say I'm just randomly starting from my a node, right? And I have my a is 1, right? A is 1, then I can just go to where do I go if my a is 1? I'm going to here, right? From there I can go to uh, OK1 if my a is again 1, right? But let's see our circuit just initialize from here where I don't have this init state part, right? I just initialize from my A1. So I don't have any previous inputs, but I have A is 1 in my first clock tick, right? It might just transition to here, right? So that is kind of incorrect, right? That's why you need this init state as well in your design specifically, right? I mean you are initializing somehow with this state, so you don't get any confusions at the beginning. But after you enter one of these four states, actually, because there is no state transition to init, right? So you will be staying in this loop, or is this these four states somehow. But this is kind of important at the beginning. Okay. So you can analyze this circuit and develop it using or implement it using VHDL if you like to do so. So now there are two input conditions. So if you are designing it, maybe it's easier to implement it as this is and let the Vivado software or whatever your synthesizer to actually synthesize the circuit for you, right? As we discussed in previous examples, it's just a cranking the shaft, right? After you have the state transition table or a state table or the state transition diagram, it is just cranking the shaft to implement actual circuitry with whatever the flip-flops you like, right? Now I have 4 or 5 states. So based on that, you can determine how many flip-flops you need. And based on that, you can uh, determine what are your excitation signals, right? Based on that, you can implement your circuit. But you can just implement this using high-level codes, so or behavioral codes, so that Vivado will synthesize it for you. Okay. Okay. Thank you.